Okay, so where we left off is we were trying to, where we left off, we'd finally come up with a way of producing a confidence interval for transient analysis or a terminating simulation. So we were trying to estimate a measure for terminating simulation, such as the expected average delay in queue over the day. So it's important to have that little caveat in there because next, after this, we'll be looking at steady state simulation. So what we did was look at independent replications of our, in this case, delay in queue. And then in our example, I'm also going to do it for utilization and the size of the queue, but just delay in queue is a good just thing to think about. So the idea we're going to perform n independent replications. Each of those, we're going to have these n observations. And from them, we are going to compute the tally average, the variance, and then estimate our confidence interval as that average of the averages plus or minus this quantity, which is called the half width. And that's the estimated as standard deviation divided by the square root of the number of observations times our t statistic, which is the quantile of a t distribution with n-1 degrees of freedom. And if we want a confidence interval alpha, we have to look at the quantile at 1 minus alpha over 2. Okay, so that's what we had. And so how do we carry that out? So again, our objective is a confidence interval for that. Our method and by method, I don't mean a Java method. I mean, this is what we are going to be doing. Is so far the statistics that we've been using, we're going to be calling the inner statistic. So we're going to create a new stats objects, and they're always going to be a simple stats tally. And so for each measure, we're going to create both an inner one and an outer one. To do our independent replications, we're just going to wrap our schedule, reset, and start simulation in a for loop. So if I want to do 100 independent replications, I just do a for loop 100 times. And each time I'm going to do a reset and a start simulation. Reset takes the simulation, puts it back in its original, puts all of our state variables back to their initial values. But then what we have to worry about is that every time we do this, the stats that we have that are listening to our component still have the data from the previous one in it. And so what we have to do is after our reset, or after our schedule reset, but before start simulation, we have to reset all of the so-called inner stats. And then when we return from start simulation, then when we take the values and when we pass them from our inner stat to the outer stat. And then after all the replications, we use the outer stat to create our confidence interval. So in the code that I've pushed in, there's now another package called mv3302.output. So we're going to use that package for looking at examples of output analysis. So we're going to take our basic multiple server queue model, and for this we need to use our entity server model because we want the delays in the queue. Now we could have used the simple server and appealed to Little's formula. Again, that would be something we could do, but just to not have additional noise in this. With our entity server, we were explicitly capturing the actual delays in queue and not kind of finessing and using Little's formula. Okay, so so to that end, we're going to have an entity arrival process. Remember, that was creating the entities and injecting them into our entity server. And for that, we're going to use an exponential distribution with a mean of 0.9, just to pick one. And then just to kind of reuse some of the things we've done recently, for my service distribution, I'm going to use a triangle distribution with these values, with 2.2, 4.5, and 6.4. And yeah, I think I was just being a little ornery here by making this inner one a float. That's just to, again, just to underscore the fact that when you make one of these random variate guides, you want to make it as general as possible. So even though internally all the values are double, it should be able to take integers and doubles and floats and whatever you have. Okay, so our service distribution is going to be the triangle that we used. And so to that end, remember, we have to add the search package so that our random variate factory can find it. Okay, so here's our entity server. It listens to our arrival process. Okay, so here's, I don't know if I showed you this back when we were doing plain old Java, but what I want to do is I want to have some flexibility about the number of replications. I'm going to have a default of 50. So if I run it from here, I'm just going to have 50. If I want to have a different number, then I'm going to grab it from the command line. So what this says is this remember our friend args that gets passed in from the command line. So if it's bigger, if there's an argument there, I'm going to assume it's an integer. I'm going to try to parse it, and that's going to be how many replications that we're going to use. So we'll show how that works in just a little bit. But for right now, if there's nothing there, I'm going to take a default of 50. Why 50? Because it's bigger than 30. Okay, so for this, we're going to kind of simulate an 8-hour day of operation, assuming that our units of time are minutes. Now, you may or may not have noticed that in SimKit, the units of time are unspecified. They're whatever you want them to be. So in this case, we're going to sort of implicitly assume that they're going to be minutes. There are 8 hours in a day, so 60 minutes. This is transient analysis, meaning that each replication, we're just going to run it for actually this is a very short amount of time compared to the kinds of other runs that we've been doing. But if this is what the store or the facility that we're modeling, this is how it operates, then we're assuming that each day is like any other in terms of the number of servers, the number of the arrivals, et cetera. All of that is something where a more detailed model might capture some of that. In other words, if, let's say, maybe Mondays are different than Fridays in terms of the way the arrivals show up, or maybe there are different numbers of servers on each individual days. If that's the case, so let's maybe take that as an example. Supposing Mondays are different, but we're going to assume that all Mondays are the same. And so what are 50 here, like if we're going to do 50, we're going to do 50 Mondays. Okay, so that's, and then if we had to do a different analysis because each of the other days had different parameters, then we would do a separate analysis for each of those different days. Okay, so again, remember, I always kind of print out our components to make sure that the parameters get there. Before the run, I also kind of print out this is going to be how long we're going to run it. This is how many replications. It's important to do that before you actually do it, because if there's an error if the simulation kind of blows up in the middle, then you at least have this information to see what was going on. Okay, so here's, but now for the important part, we're going to set up our statistics. We have inner and outer stats. The inner stats are what we've been working with so far. So the three things that I'm interested in are delay in the queue, the number in the queue. Probably should have moved this up to here just to be complete. Okay. I'm interested, I'm going to try to look at utilization as well. Again, I'm interested in utilization, not so much the raw numbers. In order to get utilization, I need to collect a time varying number of available servers. Okay, so these are our inner stats. This is what we've been working with so up to now. So delay in queue, again, property change listener to our entity server. For our entity server, remember it's since it's a collection, and I want the average number, so I use a collection size time varying stat. Again, property change listener. And then finally, in order to do the utilization, I want the number of available servers. That's going to be a time varying. So with this one example, I have a tally, a collection time varying, and just a simple stats time varying. Again, these are the inner stats. These are going to be collecting for each replication. Now, to do this analysis, for each of those, I also define an outer stat, and the outer stats are always tallies, even if regardless of what the inner stats are. And, think about why that is. See, let's look at number of available servers. So again, that's going to be a time varying stat, but when I finish, I'm going to have one average, sample average for that. But the replications are discrete. If I have 30 replications, I have 30 individual values. And if I want the average of that, then it's always going to be a tally. So regardless of what type the inner stats are, the outer stats are always tallies. And just for completeness, I just kind of put in what the corresponding inner stat is as the name, but we notice that these stats, I do not add as a property change listener, because for these I'm going to put in the value by hand, and we'll see what that is. Okay, so I set the stop time. I just need to set that once and for all. Okay, so here are our replications. Here's the for loop over the number of replications. Okay, within each replication, first I do a schedule reset. I start with that. What does that do? What schedule reset does is it invokes reset on every single simulation component. It calls that reset method. And what does reset do? It initializes all of our state variables. So this guarantees that all of our components are going to be starting in the same place with their initial values. The queues are going to be empty. The servers are all going to be available. And then it also sets sim time back to 0, and then puts all of the run events on the event list. And if we were to run this in verbose mode, then we'd just see a whole boatload of this stuff. We're not going to do that. And the thing is that prior to even doing this, we will have hopefully verified our simulation model by running it in verbose mode and verifying that all of the state transitions and the scheduling, all of that was happening correctly. So you don't even do this until you verified that your simulation is working correctly. Okay, so now notice that, and between schedule reset and schedule start simulation, there's some stuff. So you may have been wondering up till now, why do we have a separate reset and start simulation? They were always one after the other. Why couldn't we do those together? Well, this is why. Because between reset and start simulation, we need to reset each of the inner stats. And how do we do that? Well, each of those they have a method called reset. Now the stats, unlike the sim entity, unlike the event graph component classes, the reset method in the stats objects are not automatically called when we call schedule reset. And this is why, because, well, not for this. If they were, then that would be kind of useful, and maybe it's something I should put into SimKit. But here's the problem: our outer stats we do not want to reset, because if we do, we would lose all the information, all the data we were putting in. So before we start our simulation, but after we've reset everything, we want to make sure that we reset all of our inner stats. And then we call start simulation. And again, this is just a normal method call, but when you call start simulation, then the processing actually stops right here until that replication is complete. So when that replication is complete, then the processing moves on to the next. So we take our outer stats, and this didn't really need to be in a separate line. Okay, so our outer delay and queue stat, I take my inner, see my delay and queue outer stat, I take my delay and queue stat, my inner one, and I simply get its mean, and I pass that as a new observation to the outer stat. Likewise, for the number in queue, I take the mean of the number in queue stat and pass that to the outer stat here. And then finally, for the utilization, now for the utilization, I'm interested in, I need to compute the utilization. So how do we do that? Remember, that was 1 minus the mean of the available servers divided by the total number of servers in my entity server. And that will be one observation of the utilization for that run. Okay, when all of that is finished, now these three outer stats objects have the mean, they have the variance, the standard deviation, and the count, which is how many that they've done. And so with that, we can compute the half-width for the confidence interval for our delay in queue. And what that's equal to, that's the standard deviation divided by the square root of the count times our student t quantile. So now how do we get that quantile? Again, that's if we look at the import, we see that in SimKit there actually is a class which gives us a method for doing that. Where are we here? Okay, so the quantile point. Now here, this was a 95% confidence interval. So this was 1 minus 0.05 over 2. So then now we can write our confidence interval as the mean plus or minus the half-width. And similarly for the number in the queue, again, I perform the same, I get the half-width from the outer number in queue stat. And then finally for utilization, I do exactly the same thing. So if I were to run that, then, and it runs fairly quickly because we are only running for 480 time units. So 50 replications. So my approximate confidence interval for the average delay in queue is is this. 7.2 plus or minus 1.4. And then for the expected average number, it's 8.2, blah, 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 and the average utilization, 0.94 plus or minus 0.01. Okay, now the question to ask is how, is that tight enough? In other words, here, my average delay is plus or minus a minute and a half, almost a minute and a half. And my expected average number is, plus or minus 1.5 customers. Okay, is that tight enough? Is that close enough? If it's not, then pretty much the only recourse I have is to run for more. And that's where I can kind of see. What I did was I created a one of these configurations. And let's say if I give it an argument of 100 and I run it from here, then I run it for 100 replications. And you notice that the confidence interval, my means are roughly the same, but now my confidence interval is a little tighter. Now it's only about plus or minus 1 minute or plus or minus 1 customer. And is that, is that enough? If it isn't, let's just try to run the bejesus out of it. Might take a little bit longer. Okay, but now my expected average delay is plus or minus, 0.3 minutes. So what's that? That's like 20 seconds. And my expected average number is plus or minus like 0.35 customers. And we see our utilization is actually also very, very close here. So in contrast, like if I were to try to remember, say we could run this on the actual system itself. But if we did, I would need, if this were only, say, for Monday of this facility, I would need 1,000 Mondays. That would be, that's a long time. But here, it took me about 2 seconds to come up with something much tighter. And then you could ask, well, how acceptable is that? That's the average over the whole day. Maybe what would happen? Remember here we had 5 servers. Say, well, what if we added a server? What would that do to our measures here? So you see, by adding a server now, my expected average delay in queue is now cut from about 7 something to about 1 something. And my expected average number in queue is a little over 1. And notice my utilization has gone way down as well. And that's to be expected, because just in general, utilizations of above 0.9 are mean that your servers are just busy all the time, almost all the time, and that usually implies longer queues. Okay, so these are some of the what if kinds of questions you can ask of this. That is, once we have things like a confidence interval, meaning that with a fairly tight confidence interval, we can be pretty confident in our results, not just with one replication, that we can start making some informed recommendations about this. That is it worth the while of this facility, in this case, to hire another server? Maybe only for Mondays, if that's the busy day. And if they do this, we can help them enable to do some kind of cost benefit analysis. So in other words, what is it worth to have this kind of improved customer service? And if you think that, measures of waiting in the queue are not such a great measure of customer service, think about how much you enjoy waiting on queue. How much do you enjoy waiting in a, waiting on hold in a call line where your call is so important to us, but you're sort of sitting there listening to elevator music, and how does that make you feel? Does that give you warm and fuzzies about the company that you're dealing with? Okay, so just a final, so we've seen how to do it, and that is all on GitLab. But it is important to understand what the meaning of a confidence interval is, and this is review. This should have been covered in your stats class, and I'm sure it was. But it's important to understand that the computed confidence interval is not the probability. So if I have a 95% confidence interval, it doesn't mean that my true mean, the probability of that mean between those values is 0.95. That is, having confidence is not the same as probability. And the best way I've found to kind of just understand what this is about is, yeah, yeah, in and out. Yeah, that's, oops, what are you doing? Zoom is screwing me up here. All right. Okay. So just a way to think of this is that we've essentially conducted one Bernoulli trial that has a probability of success of 0.95. So what does that mean? A confidence level of 0.05 means that having conducted one of these, if we were to do this many, many times, then roughly 5% of the time, our true mean would not be within the two values we compute. In other words, or to put it in a more positive light, 95% of the time, we would have our true mean, because we don't know what mu is. We don't know what that true expected delay in Q is. 95% of the time, they're going to be between those. But we don't know which ones. And I misspelled probability because there are too many I's in it. So what we've done, I mean, here's another way to think of it. We've taken a coin that has a probability of 0.95 of coming up heads. We flip the coin, but instead of landing, it kind of rolls out the door and rolls down the sewer. But we say because the probability of success, because the probability of heads was so high at 0.95, even though we didn't see that, we're going to declare success anyway. Okay. In other words, we have conducted one experiment that has a very high probability of success, but not a probability of 1. But we're going to declare victory anyway, because we had it was such a good bet. Okay, so that it's just important to understand, because we can't say the probability that our true expected average delay in Q is between this is 0.95. We can't say that. What we can say is if we were now to do this experiment many, many, many times, that is, do this whole thing a whole bunch of times, then roughly 95% of those times, that true mean will be between these two values. So we're going to declare victory anyway, because we're only going to do this once. But 5% of the time, we're going to be wrong. And it's important to just understand that we will be wrong sometimes. Oops. Where the heck are you? Okay. All right. So that's all I wanted to cover for today. Tomorrow we're going to start looking at just some other issues with this, and maybe look at another model and look at some more complicated things. And then even with this, there are still some issues about how to conduct business. And then following that, there is the whole issue of steady state analysis, which is kind of has a whole different set of problems associated with it. Just to kind of peek ahead a little bit, the thing with a transient analysis is that the results are affected by our initial conditions. The results are affected by our initial conditions. In steady state, the results are not, or should not be affected by the initial conditions. So those are two different things. In other words, for the same facility that opened and closed every day that we just analyzed, what if instead of doing that, they were just open 24/7? I mean, what if it were like a Denny's or something? So could we, what would be our interest there? The thing is that we don't know if this system could blow up. In other words, the fact that we close the doors at the end of the day means that we haven't run our system long enough to see what happens to the queues as they go on forever. They could blow up. We don't know. We don't know because we stopped the run, because we only need to run it in this case for 480 minutes because that's all we had during the day. If we'd kept going, maybe the queues would have built up forever. We don't know. That's what steady state is about. And that's what we're going to look at in a bit. So that is it for today. And if there are no questions, we will adjourn.